Okay, thank you very much. I'd like to start by thanking the organizers for inviting me, Sebastian and Jason. Thank you very much. And so I'd also like to start by thanking my collaborators. So most of what I will be talking about today has been done by this guy, who is a PhD student, Fabian Cuela, who is studying PhD in a few months. He's in collaboration with the people from the spintronics group in my lab, Pierre Sénéor, who worked in graphene for a few years. Christian Ulysse from C2N in France, who is doing lithography, and the group of Cambridge, Stefan Hoffman, who is providing some graphene. Okay, so this is what I will be talking about today. Basically, I will be showing experiments of transport in devices in which we mix high TC superconductors with graphene. The idea is to see whether we can proximitize graphene with a high TC and whether we can measure Andreev reflection in this interface. And what I will be showing is that indeed we managed to get transparent conductance between YBCO and graphene to measure Andreev reflection and to modulate this proximity effect using a gate. And this gate actually is induced electron interference at this interface, which is kind of an analog of Klein tunneling, as I will be explaining later. So most of what I will be talking about will be published in a few days or weeks in Nature Physics, has been accepted. Okay, so I mean, you have heard already this morning about during the talk about proximity effect. If you look at the microscopic picture and you look at the Andreev reflection of these electron hole pairs, which coherently propagate and take superconducting correlations into the normal metal, if you have a normal metal, the band structure is trivial, which means that the effect is not actually affected by it. You can be in the ballistic of a diffuse regime, but the band structure of the normal metal doesn't play any role. If you put graphene, things are different. And in reality, if you have graphene, which has this well-known band structure, if the doping, the Fermi energy is high enough as compared to the Dirac point, basically you can think of the Andreev reflection as in similar terms in a normal metal, in the sense that the electron and the hole both reside in the conduction band. But if the Fermi energy is close enough to the Dirac point, then a special situation occurs in which the incoming electron to this interface is in the conduction band, but the reflected hole is in the valence band. And if you do the math and you calculate the group velocities of these particles in the different situations, you come to the conclusion that in this situation you have the usual expected retroreflection, but in this situation you have a special Andreev reflection, which is unusual, which is the so-called specular reflection, as was discussed many years ago by Villegas. Okay, so of course, going from this situation to this situation changes very much the conductance across this interface. In the usual case, so to say, you have an enhancement of the conductance for sub values of the energy of the involved particles. But if you are in this regime, basically you can have a zero conductance at some value of the applied bias. Actually, with this bias equals the Fermi energy, because this hole is kind of at the Dirac point, so you don't have conductance. Okay, so there are other characteristics of the graphene band structure that may play a role. One of them is that this linear dispersion, of course, of the energy versus K, and which is if you combine it with the fact that you have very low carrier concentration, meaning that when you dope this material, you change very much you can change a lot the energy, and then you can change a lot the K vector. So you can play with this also to change very much the conductance across this interface. So all these mechanisms, as I say, depend very much on the Fermi energy. So by doping the graphene, which you can do with a gate voltage, for instance, you can change a lot of the conductance across this. Imagine these junctions in which you have a graphene in between. Okay, of course, all of this is not new. This has been studied for many years, since the very beginning of the graphene. And also this modulation of the critical current using a gate voltage, or even this specular versus retroreflection crossover as a function of the doping of the graphene have been shown recently in a more convincing way, I think. But there is something which is something which one has to bear in mind, is that all these experiments have been done with low TCs, and this has imposed some constraints on the graphene you need to use to observe these effects which are very much related to the graphene structure. What happens is that you can think of it, if you have inhomogeneities in the doping of the graphene, spatial inhomogeneities, meaning that the Fermi energy is not the same everywhere, but in some parts you have close to the dirac point, but in some other parts you are far from it, then these effects kind of are, I don't know, smeared away or are hidden. And you have to compare these inhomogeneities with the size of the superconducting gap. So if you are using low TCs which have gaps of millivolts, then you might be in trouble, because the graphene inhomogeneities might be at least a few tens of millivolts in regular graphene. So one needs to use very clean graphene with very low doping and very homogeneous in order to observe a pristine manifestation of these effects. Okay, so actually this is one of the so to say naive reasons why one would like to use high TC superconductors for this experiment, because high TCs has larger gaps, which are tens of millivolts, and then those are, you can think even of looking at this kind of interesting effects, even with not so clean graphene, with graphenes which have doping inhomogeneities which are quite large. Of course, there are more subtle and more profound points of interest for this combination, which is that these superconductors are non-conventional superconductors, so you have a pyridine symmetry which is anisotropic, and you can think of interplaying between this anisotropy of this order parameter and the anisotropic properties of the graphene, and then play with this, and this you have some examples in this paper. Okay, so here's the motivation for trying to do this kind of experiment. Now, there has been activity in the last years on this, and here's a very recent example from one of the organizers of this conference. So basically they managed to put this graphene on top of a cuprate superconductor. This is, as far as I can remember, an electron doped superconductor, which is not exactly the way, but and then they look at the density of states in this graphene sheet by STM deposited on the cuprate, and then you can see a gap feature that opens in this graphene, which they interpret as a proximitized gap which opens in the graphene, and you have either a gap or a zero bias conductance peak, and this depends actually on the direction and on where is sitting this graphene with respect to the grains of these materials which have different nodes. So I won't get into details. You can ask Jason if you want. But we went into another direction. We thought it would be nice to do devices, just to put two contacts in the graphene and try to see whether one can measure things there. And basically, here's where the difficulty comes, actually. If you want to use the approach that people use with low TC superconductors to grow these kind of devices with superconducting electrodes and then some graphene bridge in between, then you run into trouble, because these high TC superconductors, you need to grow them at very high temperature, hundreds of degrees, in an oxygen atmosphere, and so you cannot just deposit graphene on a substrate and then grow YBCO on top, which is what people do with low TC superconductors. You cannot have to do it the other way around. You have to grow the superconductor first and then put your graphene on top. And so what I will show you is that this, I would say, the main result of my talk is that we managed to find this fabrication technique, and that actually we managed to get this transparent contrast between graphene and YBCO. Okay, so here's the technique we use. Basically, we start by growing our superconductor on SrTiO. This is done by PLD. This is something we know how to do very well. And then we put some very thin gold on top of the YBCO in situ, and this is a critical step. If you don't cover your YBCO in situ and you put it out of the chamber and you do all these chemicals that can afterwards for the lithography, the YBCO substrate, the YBCO surface degrades very rapidly, and then whatever you have on the surface of YBCO is no longer superconducting. You have some insulating layer. So it's important to cover the YBCO in situ with a very thin layer of gold. And then you get this thing, and then you do some lithography. And what you do is to pattern the superconductor, as opposed to etch the material. What we do is use ion irradiation. We use oxygen ions at 100 kiloelectron volts, and this irradiation doesn't etch the material; it amorphizes the material. So it makes that all what is exposed to this ion beam becomes insulating, and what was covered remains superconducting. Then you get rid of this resist, and then you get a sheet of CVD graphene. This is standard procedure in which the graphene comes from some copper, and then you solve this copper in some acid, and then you fish your graphene with a substrate. You dry it, so this is very nasty and very dirty, but at the end of the day you get your graphene on top of on your substrate, and then you do another lithography step and some oxygen plasma to burn the graphene which is not covered, and at the end of the day you end up with some superconducting electrodes which are embedded in an insulating matrix which are covered by some graphene.
So you leave the gold on?
Yes, I leave the gold on. Wait, I remove the gold on this in between the electrodes at this step. So basically I irradiate this thing, and then I do some ion etching to remove these 4 nanometers of gold from everywhere, so that the gold stays on top of the superconducting YBCO. Okay?
Sorry, what did you use gold etch instead of irradiating?
No, we don't do gold etch. We find it's just 4 nanometers of gold, so this goes away very easily with argon ion milling in just a few seconds.
YBCO will stay and just clean and...
Yes. When I do this, to remove the gold in between the superconducting part, this resist I use for the irradiation stays there. So I irradiate this, then I remove the gold, then I get rid of the resist, and then I put the graphene. So it's not an extra step of lithography or anything. So, okay. So and then you can attach wires to this in various configurations I mentioned, and I will discuss what are the different configurations. Okay. So basically we fabricated two generations of devices. The first one were done with optical lithography, so there are big distances between these. So these gaps were very large, so no hope of getting supercurrents through it. And then, but the idea was to test how good was the contact between gold, graphene, and YBCO, and what do we get. And also in this first generation of devices, we were using as a gate the substrate. So SrTiO is a dielectric, which has very large permittivity at low temperatures. So this allows you to do some gating, which is quite efficient, as I will show. And then there is another generation in which we use even lithography, so these distances are in the hundreds of nanometers. And on top of that, we change the gate, and we put some aluminum oxide gate, and we do some top gating. So I will show the differences and what we find. Okay. So let's start with this part. Okay, so the first thing is to characterize this backgate, and something which is very important in this structure. If you look at it, so this is just, I'm just looking at this part, so half of it, okay? Just for simplicity. So basically, when you gate this thing, you have a superconducting YBCO covered by gold, you have insulating YBCO, and then you have your graphene on top. Now, when you apply a gate voltage here, the electric field that you generate will change the carrier density only in this part of the graphene, because in this part, which is on top of the superconducting and gold, the electric field is screened by this material. This is much thicker. This is 50 nanometers YBCO, which is much thicker than the Thomas Fermi screening lens. So basically, when you apply a gate voltage, you only change the carrier density in this part here. This is important. Also, you can do you can expect some weird things to happen. This is one of the pains of this backgate thing. You can expect something to happen at this interface because of fringe field. So the electric field is screened here, but then here, so you have this step. And so if you do some calculations, you can see that you have some divergence of the electric field here. So you expect that over some tens of nanometers, the gating will be different here than far from the interface. But other than that, this is a quite interesting system to gate, because it's built in under fabrication, and if you work at low temperatures, the dielectric permittivity of this material is 10,000 or 20,000. So even if it is 500 nanometers thick, you can gate the material. Actually, you can measure which is the gating. You can do Hall effect experiments as a function of the gate voltage. And actually, from this you learn two things. One is that graphene on this material is strongly, highly doped. So you get carrier densities which are very high, 10 to the 13. This is extremely high. And also you can see that when you apply a gate voltage, you linearly change the carrier density, and you can calculate how much you change, so you characterize your gate. And also, because the doping is so high, basically, and even if you change quite a lot the carrier density, the relative change is quite small when you are up here. So basically, you end up with the fact that the Fermi energy changes that you induce with your gating are almost linear in this range. Okay, so here's some characteristics of this gate. Now, how do we do the transport measurements in the graphene? So what we do is we have this 3-point configuration. Basically, what we do in this scheme is that we inject a current across the graphene layer, and then you measure the voltage between this part here and somewhere here in between the insulator. So I'll make the claim that we are measuring the conductance of this part of the graphene, and actually, as I will discuss later, that we are measuring the conductance between this part of graphene that becomes superconducting because it's close to the on top of the superconductor, and this part which is normal. So you have kind of have an SN interface here. So this is more evident in the measurements. So when we measure these samples, we have typically two types of behaviors that we see in these 3-point measurements. Sometimes we get this behavior in which you see this is the conductance. You have a bias for different temperatures, lowest temperature and then highest temperature. So this is about TC. And so you see either an enhancement of the conductance for bias which are comparable to the superconducting gap in YBCO, and this enhancement decreases as you get close to the critical temperature. Either you have the opposite, you have a decrease of the conductance at low temperatures, and then this thing goes away as increased TC. So looking at this from far, this looks that you have a highly transparent interface between a superconductor and a normal metal. Yes.
What's the TC?
90 is 85K, 85, 90K. It's optimally doped, yes, it's optimal. Yes. This is C-axis, huh? This is C-axis YBCO, sorry. C-axis YBCO. Okay, and this looks like a low transparent interface which between a superconductor and a normal metal. Okay, so I'm going to focus on this type of samples. And of course, you can now measure this behavior as a function of the gate voltage. And here are some examples. They look similar, but they are at the same time different. So what you see basically is that you can enhance the background conductance, and you can reduce this minima that appear around the gap. They kind of go up, and you also change the width of this zero bias conductor peak as a function of the gate voltage. Actually, what happens is that I'm going to show you that we periodically change between the different states, and this is better seen in this plot here, in which we put many of those here. And so we measure. You have the gate voltage here, you have the bias here, and in color you have the conductance. So you can see that you go from this higher conductance curves, which corresponds to this state, for instance, with these green horizontal things, to these other states in between, in which you have more pronounced pockets around, which seems to be the superconducting gap, and you periodically go to one thing to the other. Okay, and so you can do cuts in this direction, for instance, and you can see that the conductance actually oscillates as a function of the gate voltage in a periodic fashion. Okay. So now, where does this come from? So actually, we found very useful this earlier work of Jacob Linder and Andreev, which actually addressed this particular case of a junction between a D-wave superconductor and a graphene. And
How do you know you have a D-wave when your proximatize?
Well, this I can discuss, but I don't know that I have. Yes, so I didn't do tunneling spectroscopy because I cannot do, but Oded Milo did it many years ago. And actually, basically, if the thickness of this gold is much lower, much thinner than the mean free path, which is the case, you don't expect the D wave to be killed. So this is so theoretically you expect this, and Oded Milo showed, like in 2004, that the propagation length of superconductivity in golds is tens of nanometers, and here we have 4 nanometers. So I don't have in principle other expectation that the other 4 nanometers as opposed to tens. Of course. No, but what I'll show you is that I don't know. I mean, I didn't do spectroscopy, but things fit as if there was D wave there. This is what I can say. This is what I will show.
While we're at it, what about inhomogeneity? Because in the beginning you mentioned your motivation is not to have a metallic superconductor, but now you have a metal.
What kind of inhomogeneity?
You mentioned at the beginning.
Yes.
You were concerned about Fermi energy inhomogeneity.
Yes, in the graphene, as compared to the superconducting gap.
Because of putting it on a metal, that's how you address it. So if you, lots of people put graphene on.
No, but what I mean is the size. I mean, the size of the gap.
Okay, with respect to the.
With the SAT. So it's not a spatial. It's spatial, of course, but what matters is the size of the gap as compared to the homogeneities in graphene. That was my point.
Javier, have you checked if the electric field that you are applying for backgating there has any effect on TC for the superconductor?
It does not have any effect. Actually, we have done for many years field effect experiments in high TC with ferroelectrics and other, and we know for a fact that above 7 to 8 unit cells of YBCO, you don't see the effect anymore because the screening length is only a couple of nanometers or so, and this is 50 nanometers.
And the YBCO says there's no dislocation, nothing like that. It's perfectly Z-axis oriented. Because one can think that you had some.
Yes, it is Z-axis by X-rays, and well, I'm going to jump to this so that it doesn't really matter. So we know very well how we grow the samples actually, and so this is another sample, but the one of the we grow here. So we know very well that those are Z-axis, and you know we have much. Okay. So anyway, we'll walk through this theory and how we can fit the experiment with this. Okay. Okay. So the idea is as follows. So the model takes these considerations. You assume that the superconducting, the graphene on top of this superconducting gold bilayer is superconducting. That all this gold graphene is proximitized and this is superconducting. This is number one assumption. And then that there is some doping here in this part, which so you give you a Fermi energy, which might be different to the Fermi energy on the other side because you are sitting on a metal and things are different. You don't know which is this value, but you can assume it is different or not. It doesn't really matter. Then you assume that you have some doping of the graphene here far from the interface, which you can change with the gate voltage. You are not changing anything here on top of the graphene on top of the superconductor. You're just changing the graphene doping in this area. And then you assume that there is some part here in between in which you have some step. So the doping, close to the interface here is different. And this might be just because this gate is inhomogeneous close to the interface, because of the effects I was discussing before, of these fringe fields, or for whatever reason. But you imagine that this is there, okay? And this is the situation, exactly the same situation as in Klein tunneling. So the idea is the following. The idea is that you have these 3 pieces of graphene with different Fermi energy and different doping, and then when the electrons go from this part to this central part, they will change the k vector, and this k vector will depend on the you will get interference in this part, and this will depend on the energy of the incoming electrons that you change with the gate voltage, and the phase that the electrons will pick in this normal region in between will depend of the energy of the incoming electrons. As I said, you change with the gate voltage, and then you have here reflection at this interface And we have transmission, but you also have reflection, and same thing in this other interface. So we will have standing waves, so you got interference, which might be constructive or destructive, depending on the phase. Actually, as it is discussed in this paper, you will have a pi periodicity, which depends on the difference of the Fermi energy and this barrier height. So you expect from this, similarly as for normal electrons, that electrons and holes, reflected holes that are in this area, will interfere and give you a conductance which will be periodically modulated by the difference of the Fermi energy that you create with the gate voltage. Okay, so this is the model, and actually you can try to, using this model and the numerical, using some numerical calculation basis on the formulas that are in this paper, you can calculate, you can simulate what will be the conductance across this model interface as a function of the bias with respect to the energy gap of the superconductor, to the phase that you pick in this interface. And as a matter of fact, what you need to produce these simulations are a series of parameters, most of which you know from the Hall effect measurement. So you know which is the Fermi energy dependence on the gate voltage in this part. You know, you can assume by looking at this, by comparing theory and experiment, that which is the superconducting gap in this material, and this also comes from the Hall effect measurements. Basically, since you know how the gate voltage changes the Fermi energy, you can do the correspondence between this and the phase, and this allows you to estimate which is the size of this region here, which comes out to be around tens of nanometers, 16 nanometers. So actually, the only three parameters that are left to make this, which is experiment, look like the theory or vice versa, are the Fermi energy in the superconducting part, and alpha, which is the angle between the D-wave nodes at the interface. So you can play with these two parameters. Basically, what you see is that if the doping here is much higher than this modulation is weaker. This is a doping which is 35, the superconducting gap here, while it is 10 times in this part. And then when you reduce this difference, so you make this Fermi energy similar to this one, then you get larger amplitude oscillations. And then when you change the alpha, basically, as long as you are not along alpha equals 0, in which you have much more pronounced peaks and dips around 0 bias, you kind of get similar things. So other than for alpha equals 0, you get reasonable similarities between theory and experiment. So actually, if this is probably the best agreement we found, which is for 400 millivolts of doping for graphene on top of YBCO, which compares to 300 for graphene on the insulating YBCO, and alpha around p over 4. Sorry, this is pi over 4. So this means that you are facing the nodes of the D wave at the interface. Then you can reproduce most of the features that you see in experiments in the theory. So you, of course, you get this alternating conductivity in which you have enhanced and decreased conductivity as a function of the gate voltage, which here appears at phase. You have this modulation of the conductance for these two cuts that I selected here. And also you can do cuts in this direction and see that the shape of the conductor curve is fairly well reproduced by the theory. So you get this enhancement, you get so this how to say zero bias peak with this decrease of the conductance below the superconducting gap, and then you see that this thing goes up and gets smeared and down and so on. So of course there are differences, but the main features, I would say, are nicely reproduced by the theory. I will say later that there are more disagreements in the higher energy range I will discuss later. Okay. Now, something interesting about this, if we believe that this model reproduces what we are seeing, something interesting about all these stories is basically you can calculate based on the model how much current is carried by normal electrons and by electron hole pairs across this interface. So this is here. So this is more or less what you expect for normal electrons. So you see that, of course, within the gap energy, you have the electrons don't contribute that much to the conductance, and everything is carried by electron hole pairs. But what's interesting is that if you get close to the gap edge, you can see that you can see a modulation of the fraction of current which is carried by electron hole pairs as a function of the phase or the gate voltage. So kind of this mechanism allows you to tune the strength of the proximity effect in the graphene. Okay, so this is the kind of the intermediate conclusions I would like to, yes?
Can you exclude just conductance fluctuations? What would the amplitude of these oscillations be? It wouldn't be periodic, but it would be pseudo-periodic.
I don't know, I cannot exclude, I cannot explain my data with this, I think.
There would be a typical period given by Thales energy and calculated.
I didn't look into this actually, but I don't see how this could change with the gate voltage in such a way. So
You change the superconductor.
Yes, I don't know. I didn't look at it this way, honestly. So I don't know. I don't know. It wouldn't be periodic, right?
You could look on 3 periods. You could look for it.
Yeah. So basically, so what I'd like to conclude from this part is that we managed to do contacts between with you and graphene, that we see some proximity or Andreev effect at these interfaces, and that we can kind of manipulate this with a gate voltage, which looks like they are related with interference effects according to this model. Now we of course. As I said, there are discrepancies. So when you look, so what I showed you before, so I was cheating to some extent. I wasn't cheating, but I was cutting we have data to much higher bias, and I was only showing bias to kind of twice the gap. And if you look at bias above twice the gap, you can see that there is kind of a dephasing that appears in the graph. It looks like you have some other things going on. And at the time we were doing this measurement, we were not able to figure this one out, but then we are doing these other experiments, and we are seeing the same thing. It's not that we fully understand, but it's more systematic. So I will show. So here we have, as I said, now we are going to replace the backgate by a topgate, and we are trying to look at things which are closer, in which the superconducting electrodes are closer to each other. Okay. So now this gate is very different in various ways. The first one is that here you dope all the graphene, not only in the insulating part, but everywhere, because you have no screening for the graphene by the superconductor. Graphene is directly suffering or screening the electric field. Okay, so you change. So it's kind of a more homogeneous doping over the graphene. This is number one. Number two, the fact that so this gate is aluminum oxide, which is grown by ALD. And number two, what happens is that the native doping of this graphene layer, when you cover it with this aluminum oxide, is much lower. So here you are around a few times 10 to the 11th, at most 10 to the 12th electrons per square centimeter, which is more than an overall order of magnitude lower than before. Okay, so you are closer to the direct point. Actually, you can measure the resistance of this, and you can gate, and you can see, this kind of behavior to suggest that you are crossing the direct point at some point. You can characterize which is the gate capacity, and you can see how much you can change. And since you are really changing a lot the Fermi energy in this case, this is not linear anymore with the gate voltage. This is important. Okay. So now in this kind of devices, it's already time. So basically, I want to show you that you can find in these small devices kind of similar behaviors in which you see this enhancement of the conductance below the bias, but you also find a series of oscillation as a function of the bias voltage. No, it's not the gate voltage here. It's the bias voltage. Okay, and this you can try to explain this with the same approach as before. Only here now the region in which you have this standing wave, so to say, is not just close to the interface. Is the distance in between the two superconducting electrodes. The only problem is that when you do the numbers, you find you expect a distance from these oscillations in bias which is much larger than the distance between the electrodes. So we think what we are seeing here, this oscillation with the bias voltage, are not exactly the same thing. Those are exactly probably oscillations related with Macmillan-Rowell oscillations in this intermediate graphene.
Did you look for any periodicity on this?
Yes, yes. Here you have. So basically, this is so here you have different distances between the electrodes, and so you can see this is assuming the Rowell formula that you can kind of see, you know, some agreement, but still. To be honest with you, we don't fully understand this because there is in Macmillan-Rowell typically you have a normal interface and a superconducting interface, and here you have two superconducting interfaces. So kind of the distance that there is a 2-factor in the Macmillan-Rowell formula that probably needs to go away. But this I need some theory guys to give me a hand with it. So looks like Macmillan-Rowell, but it's not so clear. What's clear is that this period doesn't depend on the magnetic field, nor this conductance depends on the magnetic field, this feature. So this shows that this is some you know, density of state thing. Is not just I don't know, critical currents. And then, of course, you can do the gate, you know, gate effects also here. And here you can reproduce again, so this is gate, this is bias, and you can reproduce again these oscillations as a function of the gate voltage, only you have many more of them because you are changing the Fermi energy much more. And this combines somehow with the bias and give you these funny patterns that we don't fully understand at this time. But this is ongoing work. So I'm coming to my conclusion. Basically, it's more the same. We have these devices. We have this proximity effect in graphene, which we can gate. And of course, now we are going for Jefferson effect measurements, for which we think we need much lower temperature, because if you do the numbers, Thales energy in these devices is much smaller than the energy gap. So when you do the critical current estimate, it's quite low, and we don't have RF screening, so we are doing this as of next Monday, actually. So I'll keep you posted. So just an announcing, I'm looking for postdocs, so if there are some candidates in the audience. And also, I'd like to repeat what was said yesterday by my friend from Paris. We put together this cost. Now, from yesterday to today, we even got a logo, which I don't know what it exactly means, but it's supposed to mean something. go figure. But what's important is that you can go there, you can find which, because yeah, this is a fire, and I think this is some squid, maybe, I don't know what it is. So you can go to this web page, look for your national correspondent. So there are proposals from each country. I think most of the countries are represented. If not, you can adhere, there's no problem. If your country is not there, you can adhere. And so there is money for short-term visits, there will be money for conference, so just go there, get in touch. If you don't find correspondent, send me an email, and that's it. Thank you.